Excuse me, Bryce. I believe you are on mute.
There we go, now you should hear me. Scrolls again. Screen. Okay, so I want to start off with sort of giving you an idea of the setting in which we're talking about these particular kinds of lenses. And so the setting is that we should really understand a system. So implied category theory, we work with different kinds of systems, and I want to understand a system as a kind of category, where the objects are the states of the system, and the morphisms are all the updates or the transitions between the states. So the idea is that in this talk, it's sort of more at the theoretical spectrum of the applied category theory conference, and so I'm not actually going to talk about any actual specific systems or applications, but you should just have in mind and sort of in your favourite system in my category for the purpose. Okay, and so if we have a pair of systems A and B, we can talk about this notion of bidirectional transformation between the systems. So it's something that goes forwards and backwards. And in this talk, I want to sort of model these bidirectional transformations as these delta lenses. And like all kinds of lenses, these consist of two parts. First is the forwards component. And what this forwards component does between the systems is it sort of determines when states of our system are consistent with each other. Okay? So in this picture here, say we have a state in our category B down the bottom, then the fibre with respect to this functor, which is the forwards component, is all the states and morphisms that are consistent with that state in B. Okay? And so the backwards component of our lens is going to be something which restores consistency when an update between states occurs. Okay, so here in the picture, we can see that if we say start with a state in A and a consistent state with it in B, and we make an update or a transition in our category B, then our backwards component of our lens produces a suitable update in our category A, which restores consistency. It chooses something like fibre over the next state. Okay, so that's sort of the setting in which we're working with here. Give a bit more history and context of the kinds of lenses that I'm talking about. David, again, also already gave a really good background about different kinds of lenses and how they're used in applied category theory on Monday in the tutorial. But so the term lens itself appeared first in literature, I think, in 2005, although the notion and idea of lenses themselves had been around for like 10 or 20 years before that, I think, in different ways. But really the first time they were called lenses was in about 2005. And then sort of almost directly after that, Grandis and Tolan defined this notion of algebraic weak factorisation system. Okay, they called it natural weak factorisation system, but the concept is exactly the same. 2010, state-based lenses. So this is what the name I'm calling for the lawful lenses or the very well-behaved lenses or the set-based lenses. I'm going to call state-based lenses. And in 2010, they were shown to be algebras for a monad on set, okay? On set over B, rather, so a slice category of set. Okay, so this is sort of the first instance that algebras for a monad of some kind. 2011, delta lenses were first introduced, and so these are the kinds of lenses that I want to be talking about today. And straight after that, a different kind of lens was introduced called C lenses. These are a special kind of delta lenses, and these are also shown, or rather defined, to be algebras for a certain monad, but this time on a slice of cat over a category B. Again, in 2013, just a year later, the delta lenses were shown, rather than being algebras for a monad, they were certain algebras for a semi-monad, again on cat over B. Okay, so in sort of the span of about 8 years, there's a bunch of work that's been done on different kinds of lenses and different kinds of contexts, modelling certain different kinds of situations. But we get to 2013 and this notion of delta lens is introduced, and somehow it doesn't fit in the framework of being algebras for a monad, certain algebras for a semi-monad. So that's sort of where the motivation for this talk starts. We have this sort of result in literature. Delta lenses are algebras for a semi-monad. I should say that if you don't know what a semi-monad is, it's just this word that is like for a monad except without a unit, the same way semi-groups. Okay. So we have this monad without a unit. We look at certain algebras for it, we get delta lenses. This is not really satisfying if you're a category theorist. We like things to be algebras for a monad. No one really talks or cares or looks at semi-monads at all. So that's one problem. Another problem is that because a semi-monad doesn't have a unit, there's no way that we can factorise through the free such thing generated by this semi-monad. Okay, so ordinary, if we have a monad on a slice category, we can factorise the thing we started with through the free thing using the unit of the monad. If we have a semi-monad, we can't do this factorisation. So we could ask, well, can we factorise? We have this problem, which is when can we factorise through free such delta lens on a functor? We have another problem, which is that when we look at delta lenses, this formulation of delta lenses as algebras for a semi-monad, it's not actually clear how to sequentially compose them. So one of the most important things about working with lenses is that we can compose them. If we think of them as sort of keeping systems in sequence, we want to be able to do that in sequence and get a new lens out. But it's not really clear at all how to do this when we form algebras for a semi-monad. So a lot of work I've been doing over the last few years is sort of answering this problem with different techniques, but there's been no real technique where we sort of keep the formulations out. And sort of a third problem, or maybe a question that one might have, is like, we have delta lenses as algebras for a semi-monad, which is taking a functor and giving it certain algebraic structure, but it's not really clear why or where the lifting part of a delta lens, the backwards part of our lens, is really coming from. So one might ask, well, can we get that into our framework somehow? So the overview of this talk is that these questions can all be answered with this sort of piece of pure category theory, which is this notion of an algebraic weak factorisation system. It's a factorisation system, so it's in the name that we can get some kind of factorisation, and what this is going to be able to let us do is factorise any morphism through the free such thing. Okay, so in this case, we're going to be able to factor a functor through the free lens. An algebraic weak factorisation system has an underlying monad and comonad, and so for the monad, we'll be able to see that we get the delta lenses out as the algebras for this monad. Okay. An algebraic weak factorisation system, if you're familiar with orthogonal factorisation systems, they have this orthogonality property associated with them, which is really talking about. Here we'll see that for this algebraic weak factorisation system we defined for delta lenses, the lifting property or structure rather for factorisation system is exactly describing the lifting or the backwards part of a delta lens. And finally, we get some canonical notion of composing algebras for a monad when that monad arises from an algebraic weak factorisation system. So really the talk is about introducing this technology, which is this algebraic weak factorisation system, and using it to solve these problems that have sort of been lying in the background of this notion of delta lens. Okay, so this is the structure of the talk. I've got sort of 4 main parts. I want to tell you about some delta lens background first, and then I'm going to tell you about algebraic weak factorisation systems. Tell you then about the algebraic weak factorisation systems for delta lenses, so putting together these first 2 parts, then I want to wrap things up at the end. So at the end of each part, I'll sort of pause to ask if there's any questions. Delta lenses. What is a delta lens? So I've sort of already said it a little bit. Here's a sort of more concrete definition. A delta lens is a functor. Okay, so remember we're thinking of this as some kind of way of keeping 2 systems A and B. And this functor is equipped with additional structure, and this additional structure is called a lifting operation. So the functor is giving us the forward parts of the lens. The lifting operation is going to give us the backwards part of the lens. What this lifting operation does, if we take an object A in our domain, a morphism U of this particular shape in our codomain, the lifting operation gives us a lift. And this lifting operation has to satisfy some axioms, okay? Yes. The audio is dropping out, okay. Higher, okay. All right, could I speak louder? Does that also put it a little bit higher? Yeah, I could also do that if it works. Okay, is that working? Okay, I'll keep going. So this notion of delta lens has to satisfy some axioms, which are sort of really sensible things to ask for. This first one is just saying that this lifting operation is actually giving you a lift. So when we take this phi of AU and we apply our functor again, we get back to U. The second one is just saying that this lifting operation preserves identities, okay? And the third one is saying that it preserves composition. And so I want to talk about this category. Let me see if I can move this. I want to talk about this category of lenses, but in contrast to sort of many other talks or things you might have heard considering lenses where we take the lenses to be the morphisms of the category, here I want to talk about a category whose objects are the delta lenses, okay? And I want to consider the morphisms of these delta lenses, okay? And so what these will be is if we have a pair of lenses, f of phi from A to B and g of psi from C to D, a morphism is just going to be a pair of functors which make the underlying square of functors commute and which preserve the lifting operation in a sensible way. Okay, so if we lift via phi and push that across via h, it's the same as pushing a morphism along by k and then lifting by psi. Okay, so we get this category of lenses, and it has this sort of obvious forgetful functor to the category of commuting squares, the arrow category of cat. And one of the goals, I guess, to show that lenses are algebras for a monad is to say that this functor is monadic. Okay, so let's talk about some examples. So the very familiar state-based lenses, very well-behaved lenses, set-based lenses, lawful lenses, all synonymous, are examples of delta lenses where we get just delta lenses between codiscrete categories. Okay, so state-based lens is just a function from A to B, a function from A cross B to A, satisfying some laws. And from this data, we can construct a delta lens between codiscrete categories, so categories on a set where there's a unique morphism between each pair of objects. Discrete vibrations have been considered in certain papers as certain kinds of lenses. And we can see these as delta lenses satisfying a certain property on the lifting operation. So this property is basically saying that if we lift and then, no, the other way around. If we apply our functor and then we lift, we get back to where we started. And split-off vibrations, which have been considered in the literature as this notion of C-lens, also delta lenses where the chosen lifts are op-Cartesian morphisms. Okay. We can also consider a kind of explicit example. So here's a pair of categories represented by the underlying directed graph. We have a functor between them where, I mean, if you look at the objects lying above an object there, that's how they're sent by the functor. And we can give a lifting operation where we specify which morphisms are the chosen lifts using our lifting operation. Okay, so here, for example, if we start with the object A2, we push that down by F to B2, and we take a morphism out of that, then that's going to lift to the morphism between A2 and A4. Okay, so there's some examples. And so I want to sort of recap this result that delta lenses are algebras for a certain semi-monad. So given a functor, we can define this category, which I'm calling J of F. And this category is just the sum of a bunch of co-slice categories, okay, indexed by the set of objects of the category A. And so unpacking that a bit more concretely, the objects are going to be pairs of an object in A and a morphism in U in B of that type. and the morphisms are just commuting triangles, which I've drawn as a square. Okay. And so here in this picture, I've drawn the objects vertically, where we've got the object A and then the morphism U below it. Okay, so this is a category that we can define for any functor. And there's a canonical sort of functor from this category to B, the codomain of the functor we start with, which is just given by codomain projection. So it takes a pair A of U to the codomain of the morphism U and a triangle or a square like this to the morphism V. Okay, so it's just projecting. And this is a delta lens. How can we see that? Well, if we take an object A1, U1, we look at its codomain projection, which is B1, and then we look at a morphism out of that, which is V, we can just lift that up by a composition, okay, to get a square or a triangle in J of F. Okay, so this assignment from F to this functor T of F is defining a semi-monad on the arrow category of cat. Okay, I'm not going to tell you what the multiplication of this semi-monad is because you don't really need to know it, but this is defining a semi-monad. And so the delta lenses are, well, they're algebras for this semi-monad. So what is an algebra? It's going to be a morphism in the arrow category of cat from T of F to F. So the structure of the algebra is this functor P. And it's going to satisfy a multiplication law, and it's going to make this diagram on the slide commute. But there are more algebras for the semi-monad than there are delta lenses, so we sort of need to restrict this class a little bit. And so we only take certain algebras, and they're the ones that are satisfying this extra commuting triangle that I've just made appear at the top of the square. And so what this means is that when we can pre-compose with this functor from the discrete category A0 of objects of A, which sends an object A to this object in J of F given by the pair A and the identity on F of A. And then we apply our algebra structure P. We're just going to get the inclusion of this discrete category of objects into A. Okay? And so one can unpack this structure and see that it's exactly the same as, it's containing the same data as the delta lens that I showed you a couple of slides before. Okay, good. So that's all I wanted to say about delta lenses to get started. If there's any questions, feel free to ask them now. Okay, I'll move on to the next section. So, algebraic weak factorisation system. So this is the main sort of piece of technology that we want to use to solve our problems. I want to start with sort of the more familiar notion, which is an orthogonal factorisation system. So most people will probably come across them at some stage in their category theory work. So an orthogonal factorisation system on a category C consists of two classes of morphisms, which I'm calling L and R, which contain the isomorphisms and are closed under composition, okay? And such that two properties hold. First is that we can factorise any morphism in C into a morphism in L followed by a morphism in R, okay? And second, that we have this orthogonality property holding. So for any solid commuting square on the outside, where the left-hand boundary is in L and the right-hand boundary is in R, there exists a unique morphism J, making these two triangles commute. Okay. And so we already know of lots of examples of orthogonal factorisation systems. For example, the epi-mono factorisation system on set, and also like the bijective on objects fully faithful factorisation system on cat. Another example is the so-called comprehensive factorisation system on cat, whose right class are exactly the discrete off vibrations. Okay, so we'll maybe see this a bit later in the talk. Okay, so the more general notion is this of an algebraic weak factorisation system. And so what that is, it's on a category. And the first thing is it consists of a functorial factorisation. And what that does is it takes every square, every commuting square of functors in our category C, and it factorises it. So it factorises the functor, or the morphism rather, F into an L of F and an R of F, factorises G into an L of G and an R of G. And from the extra data of H and K, it's producing this morphism E of HK between them. And everything here commutes. From this assignment, from F to say L of F, this is giving you an endofunctor on the arrow category of C. And actually we require, as part of the data of an algebraic weak factorisation system, for this to give you a comonad. And likewise, the endofunctor which takes, say, F to R of F, we want to ask this to be a monad on the arrow category of C. And so why do we do this? The idea is that the co-algebras for this comonad and the algebras for the monad are replacing the left and right classes of our factorisation. Okay. And then finally, we ask for this little bit of technical data, which is that there's a distributive law between the comonad and the monad. But we don't need to worry about that. And so the way in which this is the generalisation is which, if you take the monad and the comonad to be idempotent, so the multiplication and the co-multiplication are just isomorphisms, then we get back the notion of orthogonal factorisation system. Okay, so remember when we looked at orthogonal factorisation systems, we had this orthogonality property, which is talking about lifting solutions to lifting problems. So we have this canonical diagonal morphism. We might ask, well, how do we do this with algebraic weak factorisation systems? And so how we do it is sort of, we can get it from the structure of an algebraic weak factorisation system. So given an L coalgebra f of S, which is this top square here, that's the data plus some multiplication, commuting square, which I haven't included, and an R algebra down the bottom, we can construct canonical diagonal fillers, okay? So given a commuting square like this, where F is the L coalgebra and G is the algebra, we can first apply our functorial factorisation and then use the structure of the L coalgebra and R algebra to get the morphisms S and P. And if we compose along the red in this picture, we get the canonical lift or filler in our commuting square, okay? And so we sometimes call this lift phi of HK. And so this reuse of the notion phi for the lift is going to connect back later to the notion of delta lens where we've used it for the lifting operation. And so we can also note is that when we lift against, when we construct such a canonical lift against a co-free coalgebra or against a free coalgebra, it's exactly giving you the structure map for the algebra or the coalgebra respectively. Okay, so that's lifting. I guess the last thing that we really want of our, or expect of our factorisation system is that the classes are closed under composition, okay? So for an orthogonal factorisation system, this is sort of automatic, and we can also get this automatically from an algebraic weak factorisation system. And so here I've got F and G, and they both have the structure of an R algebra. And we want to know, well, how can we compose these R algebras? How can we compose the underlying morphisms and get an R algebra structure on the morphism H? And so how we do that is using the lifting operation that I just had on the previous slide. So the first thing we can do is factorise H into an L of H and an R of H, okay, using our functorial factorisation. But now L of H has a co-free coalgebra structure. So we can look at this square and apply our lifting operation, our lifting of the algebraic weak factorisation system in two steps. So first we have a square like this, and because we've got a co-free coalgebra on one side and an R algebra G on the other side, we can construct this lift and we can put that into our big picture on the other side, on the left-hand side. And then we do the same with another commuting square. We get a lift, and now we get this big diagonal from E of H to A. And this is exactly the algebra structure map on the morphism H. Okay, so all this is really saying is that we have a very nice wave. It's algorithmic. We can just follow these instructions and construct the composite of our algebras for our factorisation system. And so the nice thing is that we already have examples of lenses as arising from algebraic weak factorisation systems. This doesn't appear anywhere. You won't read this in a paper anywhere, but it's true that these algebras for lenses that I sort of mentioned in the history and context slide are actually monads that are arising from an algebraic weak factorisation system. So for example, if we take set, we take a function in set and we factorise it through just the product, the Cartesian product. We can always do that. Then this is giving us an algebraic weak factorisation system on set. And if we take the monad of this algebraic weak factorisation system, the R-algebras are exactly the state-based lenses that we are familiar with. The L co-algebras, or the left class of this factorisation system, are exactly the split monomorphisms. And the good thing about this example is it generalises to any category with finite products, okay? So people are always looking to generalise lenses to sort of other contexts, and so for this example, we know we can do it for any category, at least with finite products. We could also do it in other slightly general settings. There's also one on cat, which factorises every functor through a comma category. Okay, so the notation here is a bit idiosyncratic maybe, but we know that the comma category of f over the identity on B, we can factor a functor through it. And this is an algebraic weak factorisation system whose R-algebras are the split off vibrations, or this notion of C-lens. The L co-algebras are the left adjoint, left inverse functors. And this generalises to any two category now with comma objects. Okay, so we already have examples of lenses arising from algebraic weak factorisation systems, and so it's, I guess, not surprising that we can maybe also try and do this for delta lenses. Okay, so that's the end of the second part. Are there any questions on what we have so far? Yes?
Is the comprehensive factorization
also? So the question was the comprehensive factorisation system also an example? The answer is yes, because every orthogonal factorisation system is an example of an algebraic weak factorisation system. Yeah, so if we consider discrete off vibrations again as a notion of lens, then this is again an example of this notion. Okay, so now's the main part of the talk. We're going to use the stuff we've learned so far to sort of investigate this algebraic weak factorisation system for delta lenses. So I guess the main sort of nitty-gritty part is to construct the factorisation itself, and once you have that, you can sort of get the rest in a sort of straightforward way. But if we actually have a functor, how do you explicitly construct the free delta lens on it? How do you construct the factorisation? The first, I guess, main part is to construct the thing that it's factoring through, which is going to be this category E of f. And so how we do that is we start again with a functor, the data of a functor. We want to construct this category. The objects of this category are just pairs of A and a U. So the same objects that we considered in this other category at the start of the talk, this J of f. But now our morphisms are generated by two kinds. Okay, so the first kind are the same kinds of morphisms that we saw in this category J of f. They're just commuting triangles. Okay, and these will form the chosen lifts, I suppose, of our free delta lens. And the second class of morphisms are the morphisms that are coming from the domain of our functor. So they're the morphisms of A. Okay, so the category is going to be generated by these two classes of morphisms, modulo sensible things like if we have two commuting triangles and we paste them together, we get another commuting triangle. And if we have two morphisms of A and we compose them, we get another morphism of A. So it's not freely generated by these two classes, but it's generated modulo, conditions that we already know exist. So this is a category, and we have a functor from this category down to the category B. And again, this is very similar to the functor we saw before. It's just taking the codomain projection. So for this first generator here, it's going to send that to V, which is the codomain as shown. And for the second generator, it's just going to send that to F of W. So that's the R of f. What about the L of f? It's just going to be the fully faithful functor, which includes morphisms in A into our category E of f by sending them to this second generator here. Okay, so we have this very explicit construction of the category in which we're factorising through. It might be a little bit unsatisfying because we're talking about morphisms generated by. You might ask, well, what are the actual morphisms of this category without this generation business? So we can see that. Morphisms between pairs of an A and a U, as shown, are just of the following two sorts. So again, we just have morphisms which are corresponding to our first generator, and we have a sequence of generators like that, as shown. So how we understand this second sort is that we have our object U, U1, and we're taking a section, a retraction of that morphism, and we're applying a morphism W via f of W, and then we're applying our codomain U2. Okay, and again, R of f sends these to the codomain parts of these morphisms. And we can sort of compactify this second sort of morphism to this sort of commuting square now, where on the left-hand side we have a retraction to U1 and it commutes. Okay, so we can show these two sorts of morphisms are closed under composition, and if we compose them with each other, we again get one of the sorts that we have. So this fully describes the category that we're factorising through. Maybe you're like me and you don't really like explicit constructions and you want a more sort of universal property approach to how we construct this category. So that's what I want to show you now. So another way to construct this is if we take our functor f from A to B, we can construct the factorisation by first precomposing with its inclusion of the discrete category of objects, so A0 has the same objects as A. Then we can take the factorisation, the comprehensive factorisation of this composite, and what this will actually give you is this category J of f that we saw before. So it's just the sum of these co-slice categories. And then we can construct this push out as shown. And you apply the universal property of the push out to the outside commuting square, we get this universally induced functor R of f, and that's exactly going to be the free delta lens on this functor. And the category E of f is exactly this push out that we have constructed here. Okay, so this factorisation system is really coming from this nice collection of universal properties that are sort of pulled together in this way. Another nice thing about presenting it this way is that we can sort of generalise it to a more general setting. So we saw before how these certain kinds of lenses can be generalised to categories with products or two categories with common objects. We can also do this in this situation. So here we can generalise to a category with push-outs. We can see that we need them here. We can replace the comprehensive factorisation system with just any OFS, and we can replace this action of taking a category to its discrete category with any idempotent comonad on our category C, which preserves push-outs. Okay, so we have this very general setting in which we can construct this factorisation system on any category we like. And so this is the approach that the paper takes, and you can really just prove everything you need to know using these universal properties. So that's factorisation for delta lenses. We can always factorise a functor through the free delta lens. The second part that I want to talk about is, so this factorisation induces a monad, which is the monad on the arrow category of cat, sending f to R of f, the free delta lens. And so now when we look at the algebras for this monad, one can prove, I'm not going to prove it for you, that the algebras for this monad are precisely the delta lenses. And so, again, I haven't shown the multiplication compatibility for this algebra, but I've shown the unit and the structure map of this algebra. And so what we'll notice here is when we look at this data, the structure map of the algebra, P hat, I'm calling it, is a morphism or a functor out of a push-out. And we know that push-outs are colimits, so when we look at morphisms out of them, we can rearrange that data into a different way. And when we rearrange the data, we get exactly this same data for these certain algebras for a semi-monad that we had previously for our delta lenses. Okay, so just using, again, this universal property, the push-out, we can show without any real work that these certain algebras for the semi-monad that we had before correspond precisely to these algebras for a monad that we constructed. So really we can just use this old result to prove this new result, just using universal properties. Maybe you want some idea about how these things correspond to delta lenses. So the idea is that we have our functor, it has this algebra structure. We might want to see how we get the lifting operation from this algebra structure. The idea is just to take morphisms in E of F of this shape. So these are commuting triangles where the left-hand side is an identity and the other side is the morphism U that we want to lift. And we apply our functor P to it, and the output we get from that is the chosen lift for our lifting operation. Okay, so we've talked about factorisation, we've talked about how we see delta lenses as algebras for a monad, and now I want to talk about lifting. What are the L coalgebras for this algebraic weak factorisation system? This is something that I didn't know when I wrote the paper, but I've sort of figured it out since then. So an L coalgebra for this algebraic weak factorisation system, the associated comonad, is just going to be given by an adjunction where the unit of the adjunction is the identity. Okay, so that's what I've got there. But it's going to have extra structure. And what this extra structure is going to be is that if when we apply the right adjoint to a morphism in B, we get something that's not an identity morphism, we're going to ask that there exists an extra morphism from B of 1 to FQ of B of 1. It's going to satisfy some axioms. But so what's this really saying? It's saying that we have this adjunction, we have the co-unit of this adjunction, we have a naturality square for this co-unit. And what we ask for the extra structure is that if when we apply Q, we get something that's not the identity morphism, we want to ask for a chosen retraction, which makes this square commute. Okay, so one could sort of ponder and think about a bit more about what these actually mean in the applications. I'd be very happy to talk about that with some people afterwards. But the thing for us is that we already know examples of these L coalgebras. So for example, if we have this inclusion of the terminal category into the interval category, which picks out the object 0, this is an L coalgebra because the right adjoint is just sending everything to the terminal category. And the co-unit is the unique thing from 0 to 1, the component at 1. So this is an L coalgebra. And so we know via the lifting property of our algebraic weak factorisation system that if we have a delta lens on the right-hand side, F, we have an L coalgebra on the left-hand side, we can construct these canonical lifts. And here the lifting is exactly the lifting operation of our delta lens. Okay, so we see that these two things are one and the same. The lifting operation of a delta lens, or the backwards component of a lens, is precisely the same as this lifting that comes from the factorisation system. So I guess more generally the idea to have in mind is that an L coalgebra, as I've described it here, is like the most general structure that a delta lens can lift. Okay. Finally, I want to talk about composition. So delta lenses compose, this is sort of, we've always known this. How they compose is we can compose the underlying functors as you would expect, and we can construct a composite lifting operation. How do we do that? We take an object A and we pass it down to C via this composite functor. We'll get a morphism out of it, and we can lift it via the first, via the lifting operation psi, then lift it again by the lifting operation phi. But we can attain the same formula from the algebraic weak factorisation system. So again, we have this picture where on the left-hand side we have an L, rather a co-free L coalgebra. And we can go through the same steps that I showed you before to construct precisely the same lift, which is giving us the composite. Okay, so what we get from this is that delta lenses, considered in their presentation as R-algebras, rather than moving to some other presentation describing the composition, when we present them as the R-algebras, we have this canonical unital and associative composition just coming from the algebraic weak factorisation system. Okay, so lenses are morphisms. They're not just objects in a category, they are morphisms and we can compose them. Okay, I'll pause here for any questions. Okay, good, we're almost done. So, what I want to end with is just, I guess we've seen that these lenses are objects in some category, but they're also morphisms and we can compose them. And so there's sort of some underlying double category story here. We had a tutorial yesterday about double categories, so I thought I'd just sort of put this in here in case people are interested. So if you're at that tutorial, you'll know that double category is like a two-dimensional categorical structure. It has four things. It has objects, it has morphisms in a horizontal direction, it has morphisms in a vertical direction, and it has some kind of cells. And all of this data composes sort of horizontally and vertically. And so we have a double category of lenses where we have objects are categories, horizontal morphisms in this case are the functors, the vertical morphisms are the delta lenses, and the morphisms, the cells of the double category are these morphisms of delta lenses that we considered before. And so, yeah, so we have this category cat of our objects in our horizontal morphisms in this category lens of the delta lenses and the cells. And so I guess the moral here is that delta lenses are both objects and morphisms in an appropriate way, and we're doing an injustice if we consider them as just one or the other. We should really consider both. I think this is going to come up in a talk later this week, maybe Evan Patterson's talk, where we have this philosophy of things being both morphisms and objects. Okay, some future work. So I guess we've sort of seen, or I guess I've tried to tell you lots of examples of these lawful lenses, these lenses that satisfy axioms, arise as R-algebras for an algebraic weak factorisation system. And so I've listed them there. I might ask, well, do all of the examples fit into this framework? Are there examples of lawful lenses which do not fit into this framework? Do they all fit into this framework? If they don't, then maybe this sort of indicates some limitation of this framework to sort of working with or describing and understanding lenses of this kind. So that'd be interesting to know. I guess conversely, we could take arbitrary algebraic weak factorisation systems and look at their right class, the R-algebras, and see if this gives a useful notion of lens. We also have a way of sort of, I guess the terminology is cofibrantly generating algebraic weak factorisation systems by some class of morphisms that we'd like to lift against. And so this could be another way of generating lenses of interest. Some other future work, I guess. I mean, there's lots of future work, but I just want to ask some questions that were within scope of the talk that we've had today. So we've shown that we have this adjunction between this category of whose objects are lenses and this arrow category of cat. Okay, this is a monadic adjunction. We have the left adjoint, which is describing the free delta lens. I guess some obvious questions to ask are, what are the Kleisli categories for this adjunction? I mean, the objects are going to be functors. What are the morphisms of this Kleisli category? That's something you could just sit down and compute. Could be interesting. We could ask what the co-algebras for the induced comonad or lens are going to be, and maybe these are giving you something interesting. And another question we're going to ask from this picture. So I haven't explained why we're working with these CODs. This is just codomain. It's actually an adjunction fibered over cat. This is something, again, that's true for any algebraic weak factorisation system. We get a fibered adjunction. And we know because cat has pullbacks that these CODs are fibrations and everything preserves the op-Cartesian lifts. But it actually happens that the codomain functor, the projection which takes a lens to its codomain, is also an op-fibration. And I have an abstract way of understanding what the op-Cartesian lifts are, but I'd really like a concrete way of understanding them. And so that's another question one could ask. I guess what this is really saying is if we have a lens, we have a functor, how do we push forward along a functor? I'll give it a lens. I think this could be something interesting. Okay, so let's sum up. I guess the goal of this talk was to tell you about this algebraic Greek factorisation system for delta lenses. We saw how it sort of solved for problems or questions that one might have had about lenses that at least were unresolved. The first one is that now we don't have delta lenses as just algebras for a semi-monad, we actually have them as algebras for a monad. And so this really refines this previous semi-monad approach in literature. We've shown that for every functor we can factorise it through the free delta lens. And so this gives us sort of a new method of constructing examples of delta lenses. You can give me any functor and I can construct you a delta lens from it. We showed that the lifting operation or the lifts of the delta lenses against L coalgebras are sort of canonically induced from this framework. I think this gives sort of a useful perspective to have on the backwards part of a lens, and we could ask whether other kinds of lenses, whether the backwards operation is sort of arising from some similar kind of framework. And finally, we have sort of some canonically induced composition of lenses as the R-algebras, and we saw how sort of this gives a natural way of sort of proceeding towards a double category of delta lenses. But that's all I wanted to say, so thank you.
Okay, do we have any questions? Any in the room? Oh yeah, we've got one at the back there. Oh yeah, what I'll do is, if you repeat the question.
Was it me? Because it's probably easier if I come down and...
Maybe no change right away now.
Okay, so first of all, thank you for an extraordinarily integrative piece of work that's brought together lots of different threads and make them all made sense under one powerful mathematical framework, and got rid of messy stuff like certain algebras for a semi-monad, so very happy. My question was going to be, tell me if I'm wrong, but I think I'm actually going to repeat something you said and then maybe ask a question at the end of it. The very last sentence was about composition of delta lenses now makes sense. And I guess, okay, so you can explain that in a minute. I guess I wanted to emphasise that those of us who work with delta lenses in practice have no trouble composing them. And as you showed a couple of slides ago, anyone here could have probably worked out for themselves how to compose delta lenses. The problem is that delta lenses as algebras, when you have objects in a category, the algebras, how do you compose them? How to, again, integrate these things, how to put them back together. And you've resolved that one. So it looks like you're agreeing with me. You've got something to correct me about. And then the last question was kind of going to be, is there any hope that there are other examples of algebras for a monad that are in some sense composable, and might any of this technology carry across in any way?
Okay. So we already knew how to compose lenses, as Mike said, and I guess, yeah, the benefit of this is really being able to compose them as this presentation of R-algebras. I mean, I think to do with the second question, I guess when you're looking at a monad on a category, right, often the category has objects as its objects. And so we're not expecting to compose them in any way unless we have a monoidal structure or something like that. But if we're looking at a category whose objects could be seen as morphisms in some sense, then probably this category is actually arising from a double category, really. So that's one thing you can say. But if you do have the objects which are actually morphisms in some other context, then, and we look at an algebra on that, then probably we would want a way to compose the algebra structures on these objects, which are really morphisms. So yeah, one could hope to sort of look at other examples where this might happen in the wild and sort of see whether we can actually compose the algebras in this way by seeing it as an instance of, so seeing the monad on this category whose objects are really morphisms as an instance of something arising from an algebraic weak factorisation system. So hopefully that answers your question.
Thank you for this great and really clear talk. As you described, your methods are like very abstract and they work in a very general setting. And so I'm wondering, do you get other sorts of lenses by applying these methods to other kinds of orthogonal factorization systems?
An opportunity to think.
That's right. I get some thinking time as the mic comes back. So that's a really good question, and I guess that's something else I could have put on this future work slide, is like really finding more examples that you get from this general framework. Something I can say is, like, when you look at a trivial example, like the orthogonal factorization system. So let's go back to the slide so people can remember what I'm talking about. So this one here. So when we look at the orthogonal factorization system, where we just sort of factor every morphism into like an identity in the morphism itself, and we look at the idempotent comonad, which takes every object to, say, an initial object if it exists, then what this push out is doing is really constructing a coproduct, and we get the factorization where we factorize any morphism through a coproduct. And so this is also a known factorization system. The R-algebras are split epimorphisms. And so we could consider, split epimorphisms, morphisms with a chosen retraction as, a certain kind of lens, if you would like. But yeah, really it would be nice to see further examples where we sort of specialize this to different situations and get interesting notions of lens out.
Yeah, thanks a lot. I have two smallish questions, I think. Since you're on this slide, you said this works in any category with this OFS. Could the OFS also only exist on the co-algebras of the comonad, on the discrete guys, or do you need to factorize a general morphism? Okay, yes, right. And my second question was, why aren't there any non-trivial cells in the double category of delta lens? Why is it thin two-dimensionally?
Does this work? This does work. Okay, so first question. I think there's a really good observation is that really we could just use the orthogonal factorization system on the composite with this co-unit for the idempotent comonad. I don't know the answer to that though. It's really something good to think about, is like we're not really ever using the orthogonal factorization system on the entire category. We're only using it on the morphisms that are arising from this composite when we're constructing this factorization. So that's definitely something to think about more. The second question was, you'll have to remind me.
Why is it the double category?
Right, okay. This is another really good question. I guess, so there's this sort of theorem which from any algebraic factorization system, we can construct a double category where the horizontal morphisms are all of the morphisms in your category and the vertical ones are the R-algebras. And it just happens to be the case that this is always a thin double category, because the cells in the double category should be seen as sort of having underlying commuting square. And because commuting squares are just a frame with a property, it's going to be thin. And so with its extra structure on this thin double category, it's also going to be thin. So we're not getting sort of non-trivial cells out as a result.
We've got a question online, Bryce, which is, do you have computer implementations, and how are lenses different from dependent types?
No, I don't have a computer implementation of these things. If someone wants to sort of work on that and talk to me about it, that would be fantastic. I'd really love that. How does this relate to dependent types? I don't know the answer to that question.
Thanks. I was just trying to understand, from the point of view of the applications of lenses, is there a sense that algebraic weak factorization systems are are something that, let's say, you started out in 2003, I think. Should people have already been thinking, this is the application, we need algebraic weak factorization systems, and then discovered lenses in that way? Are the factorization systems crucial for in some sense, for the application?
I mean, I think they're useful because, I mean, mainly for the fact that you can factorize through them. I think it's interesting and useful to be able to factorize through the free such thing, the free such delta lens. And people have always been doing that because we'd always, I mean, in those previous examples, we've already had the monad on a slice category of some kind. We've already had the unit of that monad, which was giving you the factorization anyway. It just wasn't recognized as coming from an algebraic weak factorization system. So I think people do care about being able to factorize already, just by virtue of the fact that we're looking at monads on slice categories, and the fact that we can now see that as an instance of an algebraic weak factorization system is just giving us more to work with. So, I mean, especially knowing what the L co-algebras are, what the general thing you can lift against is, I think is something that is useful for applications, because we want to know what we can do with our backwards part of the lens, and this is sort of telling what all the things we can do are.